All right, let's get right into it. We all want a world that runs on clean energy, right? But here's the big question. What happens when that energy source just, well, turns off? Today, we're going to talk about the absolute key to unlocking a 24/7 renewable future: energy storage. You've seen pictures like this a million times. These beautiful, sweeping landscapes with solar panels and wind turbines. And the promise? It's incredible. But this image also hides the single biggest challenge that's holding back a fully renewable grid. That's it, right there. How do we keep the lights on for an entire city after the sun goes down? Or what do we do during a calm week with no wind? This whole problem is called intermittency, and honestly, solving it is pretty much the holy grail for the entire clean energy industry. So before we can even talk about the solution, we've got to get a really good handle on the problem itself. And it's not just as simple as the sun goes down at night. No, this is a very specific technical challenge that engineers are frankly obsessed with solving. Okay, so this is the term engineers use all the time: capacity utilization factor, or just CUF. The easiest way to think about it is like a report card for a power plant. It measures how much power it's actually making compared to its absolute maximum potential. And a typical solar plant, it gets a CUF of only about 18 to 22%. That means for more than 3/4 of the time, it's not making any power at all. And that is the huge gap we have to figure out how to fill. So what's the answer? Well, it all comes down to something called energy storage systems, or ESS. The best way to picture them is as giant, grid-scale rechargeable batteries. They are the absolute missing piece of the puzzle, the tech that can take that on-again, off-again power and make it totally reliable. You know, what's so cool about this is just how many different jobs an ESS can do. It's not just about saving power for later. It acts like a shock absorber, smoothing out those sudden dips when a cloud passes over. It lets us do this amazing thing called load shifting, basically storing all that super cheap solar power from noon and using it during the evening rush hour. And get this, it dramatically boosts a plant's effectiveness, it helps keep the entire grid stable, and it even makes sure we don't waste a single drop of clean energy. But look, it's not magic. There's always a trade-off. In this case, it's something called round-trip efficiency. Every single time you charge and then discharge a storage system, you're going to lose a little bit of energy. It's just a law of physics. And how much you lose really depends on the technology you're using. And that brings us to the main event, because there isn't just one type of energy storage. To make it super simple, we can think of them as three different kinds of athletes. You've got the sprinter, the marathon runner, and the specialist. First up, we've got our sprinter, batteries, specifically battery energy storage systems, or BESS. These are the fast, flexible, and sort of build-them-anywhere solutions that have just exploded in popularity, especially in places like India. And this, right here, is their superpower. A battery can react in milliseconds. I mean, that's literally faster than the blink of an eye. That incredible speed is what makes them absolutely perfect for catching those sudden drops or surges in power, acting like a stabilizer for the whole grid. And remember that efficiency trade-off we talked about? Well, batteries are fantastic here. At 85 to 92% efficiency, you get almost all of the energy back that you put in. This makes them perfect for that daily cycle, charging up in the sunny afternoon and then pushing that power out in the evening. Okay, so that's our sprinter. Now let's meet our second athlete, the marathon runner. This is pumped storage hydro. And this isn't a chemical battery at all. It's a massive water battery that uses the oldest energy source there is: gravity. The concept is just brilliantly simple. When you have extra cheap power, like from solar panels at noon, you use that power to pump a whole bunch of water from a low reservoir up to a high one. That water just sits up there holding all this potential energy. Then, whenever you need power, you just open a valve, let the water rush back down through a turbine, and boom, you're generating electricity. Now, here's the really key difference. While batteries are great for a few hours, pumped hydro is built for the long haul. We're talking about supplying steady power for 6, 8, even 12 hours straight. And these things can last for 40, 50, even 80 years. The catch? Well, you can't build them just anywhere. You need the right kind of hills, and they take a long, long time to build. All right, and finally, we've got our specialist, thermal energy storage. Now, this is a different beast altogether. It's not really about storing electricity, it's about storing heat. The best way to think of it is like a gigantic industrial thermos. So the most common way this works is called sensible heat storage. You use solar power to heat up a huge tank of something that holds heat incredibly well, like molten salt.
and you get it screaming hot, like over 500 degrees Celsius. That stored heat can then be used later, either to make steam and spin a turbine for electricity or for all sorts of industrial stuff.
And this is where its specialty really comes into play. While you can use that stored heat to make electricity, it's most cost-effective when what you really need is, well, the heat itself. For industries like textile mills or food processing plants that need a constant, steady supply of high-temperature heat, this is an absolute game-changer for getting off fossil fuels.
So we've met the team, the sprinter, the marathon runner, and the specialist. How do they actually stack up against each other?
Let's just lay it all out. If you need a lightning-fast response for just a few hours, like smoothing out a solar farm's output when clouds roll in, you call the Sprinter, BESS. It's super efficient but has a shorter lifespan. But if you need to store a massive amount of energy for half the day to provide truly reliable round-the-clock power, you need the Marathon Runner, pumped hydro. It's a little less efficient, but it'll last for decades. And if your main goal is just constant high-temperature industrial heat, then the Specialist, thermal storage, is your guy. You see, there's no single best solution. It's all about picking the right tool for the job. So this all sounds great in theory, right? But is this stuff actually happening? You bet it is. These systems are being built right now at a massive scale. Let's take a quick look at a couple of huge projects in India to see how this works in the real world. First, here's our Sprinter in action. At this Tata Power project, a huge battery system just soaks up solar power all day long. Then, during those peak evening hours, when everyone gets home from work and turns on their lights and TVs, it pushes all that clean energy back to the grid. It's a perfect real-world example of that load shifting we talked about. It makes solar useful long after the sun is set. And now, here's the Marathon Runner. And this thing is just enormous. Green Coast Pinnapuram project in India is this massive integrated system. It uses solar, wind, and a giant pumped hydro system all working together to deliver reliable, 24/7 clean power to its customers. This is exactly how you make renewables act just like a traditional, always-on power plant. So what's the real impact of all this? The bottom line? Just look at this chart. A solar plant all by itself, remember, has a CUF around 20%. Now you add a battery to it, and suddenly you can boost that effectiveness up to over 70%. That's a huge jump. But then, combine it with a massive long-duration storage system like pumped hydro, and you can get that plant working productively for over 90% of the time. You have effectively turned an intermittent power source into a 24/7 powerhouse. That is the power of storage. Which really leaves us with this final thought. Look, building out this level of energy storage is a monumental challenge. It's expensive, it's complex, it takes a ton of engineering. But as we look towards a future that absolutely demands both clean and reliable energy, the real question isn't whether we can afford to do it, it's whether we can afford not to.